My name is Janez Plavec. I thank Jana for a kind introduction and organizers of the school to have the opportunity to present. We already saw that this might be valuable from several aspects. I think we should have a sort of pointer or something, right? Is it spotlight is a good way now? I forgot. What's a good way to have? Annotate. Error? Annotate should be a good way, right? Or is it? Okay, I'll use that. So what I plan to do is, in this introduction section, guide you basically through this, not in detail, of course, but what NMR is, what spectrometer is. In fact, just touch upon making a sample. This is a liquid state and get a simple 1D spectra that actually tell us a lot, but cannot give us full insight. Then a little bit we'll just mention, we'll not have time to elaborate, what we call pulse sequences that give us this multidimensional spectra. And then, sorry, this stopped working. We need some model, usually done with computer nowadays, that gives us insight into structure. Here we have a simple protein. It should jiggle and jump around exactly to indicate what I'll be coming through. That NMR is a unique tool, I mean, compete is not a good word, providing complementary information to other techniques that give high resolution insight into structure details, but furthermore give dynamic information. And dynamic, I'll explain as we go along. Oh, what is this now? This was not a good way. It's not moving forward now. So I don't want to annotate. But where is pointer? Okay. But this should move on, no? I'm sorry for this. What do we do to get out of this? We just mouse? Okay. Okay, sorry. So outline. This should go away, my name here. Right, yes. So today's talk, it's a 45-minute. I'll introduce, or I did that a little bit. I'll give a short overview what NMR stands for, nuclear magnetic resonance. I a little bit illustrate through few snapshots what we can all do. It's in no way complete because we could talk for a day about that. Then I introduce terms, magnetization down to signal detection and so on. A little bit go to the spectrometer setup, although this will be nicely introduced by my colleagues, Primoz and Damian, along the school. I think we'll have even videos being presented. We'll continue with introduction what is called chemical shift, J coupling constant. I'll touch a bit about sensitivity because are typically issues that come up when NMR is considered being traditionally a method that's a little bit less sensitive in some cases, but I won't exactly show you that this might not be the biggest problem nowadays. And then as this had a subtitle solid state, Professor Mali will give more detailed information into material. I just introduced two of the interactions, dipole-dipole and chemical shift and anisotropy towards the end of the talk. And next talk will be more biologically oriented, going a little bit deeper in multidimensional techniques and other techniques. I probably will talk about quadruplexes as an example that I'll illustrate all these techniques. A course like this to get a little bit deeper insight would take at least 30 hours. We have two, so we'll give you a little snapshot, but as a teaser to maybe, as was clear earlier, to get in touch and maybe start using NMR as technique. So I represent Slovenian NMR Center, as was kindly introduced by Jana. We are very proud to be partner facility of CERIC. And NMR, as I said a few times already, it's nuclear magnetic resonance. What it goes for is this number of hundreds of megahertz. Hello? Is everything okay? I hope so. So we have now 600 megahertz that are modern, I mean, up to date. Of course, it's not top of the standards. We wish to go further, but you can see in terms of instrumentation. In terms of personnel, proper expertise is there. As indicated by earlier speaker, you click on CERIC portal or you click on ours and you'll get contact to get in touch. And my team and myself will be certainly helping you to guide, as we all do. Just a little go through. We are a center that, of course, offers access, service, but also sometimes to non-experts all the help needed, both to set up the sample, set up the acquisition of data, and then interpretation. I don't think we'll go through all this, but you can see that we go all from biomolecules, all sorts of, and what is sort of very modern nowadays, energy storage, CO2 fixation, and then hydrogen storage, polymer, and at the bottom here, not least important, is authenticity of food. We have some experience already with honey, but been working on wine analysis. This does not mean consuming large amounts of wine, by doing NMR analysis on details. I promised you a little bit historical, so in the 30s, 40s of the previous century, physicists came up with these fancy experiments that sort of clued to new technique. And end of Second World War II, very famous people, Bloch and Pascal, or their groups better, got their signal. One of paraffin, the other of water. It's an ethanol molecule here. First, of course, was big exotica, and no real use of it. Of course, was very important for physicists. But already in 1949, chemical shift was discovered. At that time, if you read papers from that time, physicists would say, well, at that time, we really understood that chemical formulas make sense. So term state, it's probably nowadays sometimes confusing to use it, but it's still there. You see, just a decade later, we have what's called high resolution. High resolution, we usually refer to the atomic detail structure, just as a rough estimate. And then a big step forward is pulse Fourier transform. Till that time was CV with its limitation of reproducibility and several times. And this is postdoc Richard Arens, and this is Professor Richard Arens, a Nobel laureate. He started his career in Varian. Varian was a big inventor at the time and definitely bringing the NMR field forward. 1974, proposal was made. This is very interesting. At the summer school on Adriatic coast. This is the same in name, Richard Arens and Jean Janez, that introduced two-dimensional NMR. And that opened really a new field, a new era in at least biomolecular, and nowadays also in solid state NMR. These are actually notes from those days. Towards 80s, NOSI, so experiments that correlate through space, was introduced, and this actually is quite important. And Professor Wittrich, another Nobel laureate, in the 80s introduced NMR of proteins. At that time, it was always believed that NMR a little bit helps or adds some detail with high resolution structure. But in the 80s, it was the group of Professor Wittrich that really demonstrated in parallel to crystallographer that actually data, results, experimental observations we get from NMR can help to build a model. I don't know you, the audience, but it works a little bit like you take a meter and you measure a certain object, like distances from a corner. So you have height, you have length, you have height, you have a little bit of inclination, position of wind and sun, and you will have from few of these distances, perhaps few tenths, you'll have quite good model of a given object, a house here, right? If you go in biomolecular world, of course, you will have these interatomic distances that help to fit in space. The only little challenge is that for what we would say small protein of 20 kilodalton, this is reasonably sized, you'll have thousands of this. So there is absolutely no way that you'll do it by hand to have a solution that will fit all this. But with some computer tools that are nowadays available, you can do that. So things, of course, evolved. In 90s, we have three-dimensional NMR, really open new venues, and then you will say just before 2000s, high field. Nowadays, we're at 1.2 gigahertz. This is more or less matter of last and this week. And you had experimental, the way we perform experiments, Doc throws it. What comes down to it's having the sharp lines for bigger and bigger proteins. And solid state, this I have a little example that nowadays, of course, you have proteins that you cannot dissolve. It's not a matter of being able to make them or afford to make them, but they are not soluble, like amyloid plaques or some membrane proteins. They don't dissolve in water, so you have to do something. And then we have MRI that are a little bit touched upon too. So magnetic resonance people or nuclear magnetic resonance people are quite proud. These are the Nobel laureates. I mentioned most of their names. And you see that magnetic resonance imaging that's used for medical applications and many others, of course, this also has partners all this development. So a little motivation that I promised at the beginning, why would one go and learn NMR and try to use it? For synthetic organic chemists, that's obvious. You want to know structure. It's not like many years ago. And this, I like this example. I don't know if you tried William Pear. It has a wonderful taste. It's a strong liquor, but the compound that gives a wonderful smell is this ethyl ester of the canoic acid. Formula is here. And anybody that has a little bit chemistry will realize that we have positional isomerism. And if you have studied, you would know that this double bond would isomerize on light. So we had, several years back, we were approached by a local company here that, of course, realized that this cis isomerism, when you keep your drink on the sun or it's being transported, you get many more. They were chromatographers and they didn't have standards. So they came to me, and at that time through NMR, we were able to show them exactly that we have this cis trans and so on and so on. So this is a little example. Of course, we did more, but to tell you the truth, the biggest challenge at that time was that, of course, any drink, it's mostly water. This is a strong liquor, so it's like 40% of alcohol. And then the compounds you're looking at are really minor compounds. This has improved over these years, how you treat these small amounts. Then dynamic processes, I touched a little bit on this. Typical problem of this is you have equilibria. So a given compound, molecule, or complex will have two states, and you want to know equilibrium constant. Then you have, this goes, of course, identifying the two, but then also understanding at what rate they exchange. And this is becoming our understanding of this process. The importance of dynamics is more and more important. Then along these lines, you have a ligand that would bind to a binding site of a given beast, and consider nowadays we're working a lot with COVID and try to find cures. So this is a way to do it. So try to understand how a given compound that might be drug will bind there. Then a little example of an amide. You see that position of red and green methyl group. Of course, they're not red and green in NMR sample, but a different position will come up and we'll be able to understand this process. And this is important, believe me. And all this then brings us to more and more complex problem, trying to understand some biological phenomena and go along. A little bit mentioned that high resolution NMR studies started in 80s with studies of smaller proteins. That's still active area of research, also in nucleic acid field. Understanding interaction and structural details. You have a piece of DNA and a protein bound to it. And then, of course, this again gives us into intricate details of a given process here, intron excision, but that's not the most important, just to give a little bit flavor what we can do. Then, of course, I mentioned in between that solid state, and traditionally, this is quite, sorry for Slovene. So you would know that for pharmaceuticals, it's very important what is the crystal form. One is for IP issues, the other is for bioavailability. So of course, one is admiring these beautiful different crystals. I don't know how well you can see. It's more cubic size or more like a dusty place, not crystalline. But when you want to get insights, what sort of hydrogen bonds are formed and how do this assemble, you see that carbon NMR shows you these differences. And of course, this is the first step to go forward and understand how do they combine. A little note, nowadays, and nowadays it means last 10 years, two-dimensional NMR has really evolved, and nowadays many groups around the world would be able to do high resolution structure in the solid state, in the powdered form or crystalline form, exactly analyzing this sort of correlations in two-dimensional spectra, providing restraints. I did mention that magnetic resonance imaging is, I call it a little cousin of NMR, of course, providing atomistic or details, anatomic details of the process, of course, being complementary to X-ray scans or CP, and looking at the soft tissue, so really complementary. Of course, here you can go much further. Functional imaging, so where in the brain does signal occur and how do we feel it? Angiography, so there's a blood clot problem. This is the way that they will inject a little contrast agents and see where the clots appear. So really magnetic resonance, you can see it's really widely applicable. And I think that would be motivation. I didn't touch on battery science and so on, because I'm sure Professor Mali will introduce those. So traditionally, when you had, this is a glycine, this is one of the simplest amino acids. You see carboxyl, right? CH2 and NH2 group. You dissolve it in solution, and this is carbon labeled. We'll come to that. So basically, it gives you a very sharp signal. But when you did that in the solid state, and you see the chemical shift range, will of course come to 200 ppm, you see that signal here covers more or less complete range. So 30, 40 years ago, this would be considered, what shall we do with this? This is useless. And of course, I will come to this. What are the interactions? We need a little bit theoretical background to understand all this. Understand this is a course, so if you will Google NMR or NMR literature, I don't mean Wikipedia and so on, you'll get some good monographies. This would be considered like Bible. Jeffrey Bodenhausen, really detailed physical or physical-chemical insights, and then you have more application like, and of course, this is no way complete. If you would, of course, this, I think, notes will be available for chemists and so on. This is a wonderful book by Professor Keller, Malcolm Levitt, very nice, readable, physically correct. I mean, physics and not the other way. So you get basics, but not given some funny shortcuts, very readable, not even for non-physicists. This is more application, showing both theory and examples, how to use it. Jacobson, this is very nice, very detailed if you want to understand how certain experiments work and what you can do. I have to show this one, late Professor Bertini. We assembled, those quotes are there, but several fields of spectroscopy used for graduate students. So this book is given a little bit of tips and tricks. So it's wonderful if you want to experiment, take it and you'll get wonderful insights. So a little bit touch, why would you bother? So crystal packing artifacts, of course, when you dissolve a given compound or mixture or whatever you're studying, that will not be the effects. You study in more or less closed environment. That's philosophically relevant, very easy titrations. And then it's another big motivation, a little bit touched upon, you get insights into dynamics. That means how the molecules tumble, and also, of course, that certain parts of the molecule might tumble differently or exhibit different dynamics than the overall molecule, and this becomes functional. And of course, this is not just for bioworld, for sure it will be for any diffusive process in the battery or a CO2 fixation, it will work the same way. Protonation state, this is a big thing when you do biomolecules, chemical shield environment, and this we will come to when two molecules interacts or a molecule will take different shape. I a little bit showed you conformation exchange. This will be the way to map them, to know where they occur and how to get inside. So when you go and you open a book, you will see that you need a spin. And nuclei that have a spin have either odd atomic mass, and they have a wonderful property, they spin 1/2. This is a quantum property. And typically for bio, you see proton, we say proton, we mean isotope of hydrogen with 1 electron, right? Carbon 13, nitrogen 15, phosphorus 31, even and so on. And here I think we will be exposed to nuclei that are very important for zeolite, battery, lithium, silicium, and so on. And then there are some atoms that don't give NMR. So this was carbon 12, oxygen 16. So I would usually make a joke that the fathers of NMR were lucky because C12, which is really 99% populated, was not given a signal. But don't get confused. Every element in periodic table has at least one isotope that's isotopically, that's NMR active. So whatever nuclei you want to study, there is a way to do it. Of course, with nuclei that have the radioactive decay in a matter of milliseconds, that might be a bit challenging for many reasons. So we are in the, to continue, we are in the quantized state. So if you have a spin, we'll have magnetic number, a magnetic quantum number related to it. And if you are dealing with spin 1/2, 1/2 minus 1/2. This will be the two states. Of course, if spin number is, I don't know, 5/2, there will be several more. And then it's related properties, magnetic moment. So we are talking about nuclei. It relates to spin with gamma. Gamma is gyromagnetic ratio. It's a basic constant of a given nucleus, of course, of a given isotope. A little bit, I don't know how you're familiar. If we sort of consider Earth and Earth's magnetic field, and in the old days we had magnets with needle, those will orient and show us north and south. It's a little bit like that in this atomic. Of course, it's a very rough approximation, but this approximation helps us, at least for the basic. So if you have these tiny little atomic magnets that are not oriented in any particular way, when you put them in large external magnetic field, this is B0, will have two orientations, with the field or against the field. And this gives the two energy values. They are called alpha and beta. This will, the sign here is up, oriented with the fields a little bit more energetically preferred. This changes with different gammas, but let's not go too much to details. Energy of the two states is a scalar product of magnetic moment at external magnetic field. And of course, the property that you would be interested in is how much more is there in the lowest energy state compared to that, and that's a very small number. At a given magnetic field, it will turn out that 1 in the 10,000, if not 100,000 molecules, it's only a difference. And that's why NMR is sometimes considered a low sensitivity method, but we'll come to that. So of course, if you are doing any sort of excitation resonance, you want to know the energy difference between the states. It comes down to gamma, gyromagnetic ratio. That's a property of a given isotope. H, Planck constant that you all know. B0 is our magnet. So how do you increase this energy difference? Sort of already suggesting or hinting at higher sensitivity. You need bigger B, B0, bigger a magnet. And that's why it's important to prove sensitivity. And of course, it's up to you which nuclei you will study. Of course, you might have some nucleus like gold or whatever in your material that it's extremely important. Of course, you will look at gamma of gold with, I think, 2 isotopes. And then, of course, you might take longer and longer time. But if you have a chance to consider, oh, shall I look at proton or carbon? 4 times bigger gamma of proton, the comparison to carbon, it means you'll probably go for more sensitive nuclei. But of course, this comes down to experimental details. So if you consider Planck relation, this delta E that we calculated, you see the frequency or omega in rotating frame. It's a very simple relation. The basic equation of the NMR is omega 0, it's gamma B0. So any nuclei has a gamma, it's a basic constant. A magnetic field is the magnet you're using, so you know the omega that comes down. So NMR has this unfortunate name, nuclear, and people would consider that we are having to do something with whatever excision of internal electron and so on. It turns out this is just a nuclear, a property of a nucleus of an atom, right? So the frequency we are dealing with are very much in the radio range. So far, far away, 10 to the 10. So 10 orders of magnitude away from anything kicking out internal electron and so on. So really non-invasive in this sense. Here is a little list of nuclei. I did mention already that you can pick any nuclei, any element in periodic table gives signal. Typically, we consider proton NMR, 1H, very highly populated, big gamma, which has big sensitivity. What is interesting, spin 1/2, so it has 2 states to magnetic in our little model of representation. So with the field, against the field. Deuterium, some people, especially beginner, would make a mistake. The deuterium is not. It is NMR active, it has spin 1. That means that it will have 3 orientations. You see natural abundance is lower, gamma is lower, so it's already creating a little bit of challenge. But believe me, wine analysis is done exactly by recording deuterium NMR spectra. C13, it's very important when you deal with organic or biomolecules. You see 1%. Nitrogen 15, it's another nucleol. Phosphorus, of course, also a molecule of life. A little rough presentation that might stay in your background. So proton is very sensitive. Carbon 4 times less, nitrogen 10 times less, but still is the way we would design experiments. And also to look, when I was a student, we would think, oh, nitrogen is hard. Nowadays, we have so-called inverse technique, so it's not such a challenge. And of course, sometimes you do want to see exactly what is happening at a given nitrogen atom in a molecule, then you will do nitrogen detection experiments. So how do we envisage? I show you a very simple explanation earlier. So we consider our spin angular momentum. This is not a spin. Spin is a quantum property, right? So, but these are the models, simple models that help us to understand. So when you have a nucleus with magnetic moment, you put in magnetic field, it will try to orient it with the field, but because there is a vector product with them, you get precession. The vector product, of course, will try to orient it in that way. So it's like 2 forces, one orient with the field, the other rotate around, and precession is a sort of the model. So what comes down to, so you have this individual nuclei with magnetic moment, but our sample is not consisting of 1 nucleus, right? It's 10 to the 23 of Gardner number or so on. So you have some that are precessing with the field, some are with opposite field, minus that in this coordinate system. And what comes down to is that when you sum these two, so what is the ensemble average of this? We get equilibrium magnetization. That's the term we use, and we usually label it with M0. And this is the property of a molecule, of our sample, of a given concentration. And this is our equilibrium state. M0 points along z-axis. So to do an NMR experiment, you will need to tilt it. And we do that with pulses we create along x, and that will sort of, in a vector model, make this vector move away or move into xy plane with a pulse. And that, of course, after vector has been sort of kicked into XY plane. If we just leave it, it will go back. But every moving vector will create a current in the coil in XY plane. And that is NMR signal. It's called free induction decay, FID. Again, unfortunately, if you Google nowadays, FID means many things, but this is NMR signal, so current or voltage along time. In a matter of here, it's pretty long, in a matter of 0.7 second. Of course, this is hard to interpret. So we do frequency analysis with Fourier transform, and we get spectra in the frequency scale that whoever has some insights into molecules will understand and will be able to read this or interpret in terms of molecular structure. The way we typically present an NMR experiment is, as we said, just a little sort of go through. We had M0 that we do with pulse, we incline to XY, and then we acquire the signal. So this becomes good for teaching, but very impractical for when we discuss which experiment to use. So these are typically labeled like this. So you wait, you excite, and then you detect. There's a little time, but this is no way in ratio. So we wait seconds, and depends how which nuclei. This is microsecond, this would be nanosecond, and then we again detect seconds. And this is the very basic 1D experiment that tells us a lot. So we did come along. Omega 0 is gamma B0, and the given nucleus has a signal, and that would not be very useful. So you want to study a molecule, I don't know, let's be an ethanol, knowing that it has a proton and carbon inside would not be very useful. So what early on was discovered that electronic clouds around a given atom that's given NMR signal can be of different shape, can be more or less, I will use the term populated, and of course electrons circulating or tumbling or whatever you would say, create a little local magnetic field that might oppose or add to external magnetic field. So the net or effective field felt at the nuclei, it's a B0, that would be in Tesla, minus a little term that we call shielding, chemical shielding. And that will create that if electron cloud has been a little bit delocalized or added to it, I mean, the nuclei will feel different magnetic field, and of course their resonance signals will appear at different positions. And that's this beauty, right? So if you're looking at an ethanol molecule, you get a meta, you have a signal for CH2, you have a signal for OH group. And chemists have developed all sorts of models and methods to explain. OH oxygen will pull electrons from hydrogen, so it's less electron rich in comparison to CH. And that's why we get this move to low field, we say, and the other way around. And there are many, many more. So you have a aromatic ring in that molecule, and of course that will again create certain different things. What turns out, if you speak in terms of frequency, that will be very hard, because probably not two spectrometers around the world have exactly the same frequency down to the 6th or 7th decimal of sub-hertz. So what people came up with is this was called chemical shift, so scale, chemical shift scale. So you're taking a difference between the frequency of a given group or signal, and you take reference away, and you divide. So you have ppm, parts per million. And this becomes transferable. What you need is a reference, an agreement, and typically this is a molecule, tetramethylsilan, which we would add a little bit in solution, and any difference in signal position with respect to this molecule that we all use, nowadays also, of course, is done by computer, position will be expressed in ppm scale. And for somebody with a little bit chemistry background, this is great, because you have here on this scale, this is a proton scale, 0 to 10, 15 ppm. You will have groups that would have inductive effect, positive, so will increase electron density, or groups that will pull away electrons very much, like carbonyls, formaldehyde, and so on. And they will the localized electron. So, and this goes very well along with this chemist notion. That's why I say chemical shift as a term. It's in a way very, very instructive, very useful, because this goes very well also with reactivity that, of course, organic chemists or synthetic chemists use. Just a little hint, you see this is C13 chemical shift scale. And you see aliphatic, aromatic, CO groups. It's very much the same, right? So it's sort of universal. Only also note, however, why would you look at carbon? You see the chemical shift scale, excess of 200. Proton is about 10. So chemical shift offers you much bigger frequency range, and that's of course motivation for this. So we talked about chemical shift as one interaction. The other very important interaction is scalar coupling, J coupling. So consider that, so we take a little example like this. So 2 carbons and 2 protons, and they of course feel themselves magnetic field of B0, but they also feel that their partner here along these 3 bonds might have different orientation. And that creates a little, let's say, disturbance. Physicists would say second order effect. So the signal in the spectrum will not be a single signal, but will be a doublet. And that will indicate for one that it's interpreting that this particular atom has at least one neighbor, or actually exactly one neighbor, that's coupled to. And that partner will also have the same. So this is a wonderful tool to identify such sort of groups. Just a little note, this for beginners is a problem. This also works with heteronuclei, and it works with single bond. When you start reading, typically it would be this, but this of course general. And then it's more, so if you have an atom next to a methyl group, it will fill local environment of 3 protons. That of course can take statistically any of the 3 orientations. So you get what we call a quartet. So observing such a pattern in the spectrum will tell you, wow, I have a methyl group. These intensities grow with Pascal triangle. I don't think it's very important, or for time reason, I don't want to spend time on it. I will touch upon a little issue here. So we know now chemical shift interaction, so position of a signal in chemical shift scale, and then we know that 2 nuclei A and B here are coupled. But what happens when their chemical shift become close to chemical shift, I mean coupling constant comes close to chemical shift difference, we have this second order effect, and if it becomes even worse, you get to 1 signal. And you will see immediately what I'm talking about. So these sort of interactions are very informative. They will help us to understand which isomer we have, and so on and so on. But coming back to this issue of chemical shift and coupling constant, this is again a little illustration. So consider a molecule with 3 atoms with respective chemical shift, and A is coupled to B, B is coupled to C. So at the higher field, 400 only here, you see we have C at 2.08, B at 2, and A at 1.89. And A is coupled to B, B is coupled to C. And those, the B protons, of course, have neighbors both. You see, when you go to lower field, chemical shift has no change. Coupling constant have no change, but it becomes very difficult to discern which is which. And this certainly is one reason why would you want higher field, to get better resolution. I did say earlier on that higher field, higher B0, higher megahertz or gigahertz nowadays gives you better sensitivity. And this example shows us that it also gives better resolution, and this becomes extremely important. Another challenge that I touched upon is poor sensitivity. So with that traditionally and still nowadays, but I think people just using computer, it's hard to imagine what signal to noise ratio actually means. But in very simplified terms, you measure the height of a signal, you measure the average noise level, and you make a ratio. And you see, then in the old days, would you dare to say this is a signal and say, yes, you have this molecule in your solution, methyl-ethyl ketone here. You see, you repeat this 8 times and signal become more and more. So we have a way to get very good information, unequivocal information with number of repeating of our NMR experiments. It goes, noise scales with square root of number of repetitions. So that's why we would record spectra or perform our experiments on and on again. You will remember the slide. We touched upon how to make solid state experiments more valuable, how to get atomistic detail of the experiment, right? So the one thing that now we understand, if we have a given nuclei in external magnetic field is 0, that's always a long sag, and there's another nuclei. And these are like tiny little magnets that also interact between themselves, and that's dipole-dipole interaction. In Hamiltonian, it's expressed like this. This is dipolar coupling constant D, 3 cosine squared theta minus 1. It's a term that relates orientation of this internuclear vector with external magnetic field, and these are operators of one and the other spin. And you see dipolar constant, these are magnetic moment. What is important here, gammas you recognize, so it's zero magnetic ratio of the two nuclei. But what is important for us is this R, interatomic distance. So this will be the way to get distances between atoms. And this will very much, as I showed you earlier on with the house, will be information that will help us to do three-dimensional model. So why was traditionally very hard to get, and all this dipole-dipole interaction go above chemical shift range. And you can imagine small crystals that are oriented in any possible way, of course, with respect to the external magnetic field, and their position in the spectrum will be different. So you would observe something that's called in the literature powder spectrum. So all these tiny little contributions will sum up to a shape like that. Of course, you want to get rid of this, or you will see later you want to do, but this becomes extremely important. We said distance, but also an angle, so inclination with respect to external field. So imagine you want to understand how does a given molecule enter a cell, cross the membrane, and you have ways to get this angle. Does this species lie on the tube? Does it go in perpendicular, or does it go in a given angle? And of course, these are, in a given case, is very useful information. Another interaction that was a little bit mentioned is chemical shift anisotropy. So chemists have trouble. I mean, when I had this slide of electrons jumping around a nuclei was spherical symmetry. Unfortunately for this, it's usually not. It's a tensor property. But when you look at solution, isotropic tumbling averages this interaction to 0. But when you have oriented stuff or preferred orientations, here is a little example of fluorophenyl. You see the different orientation, different element of the tensor will give a signal. And again, you can imagine they're not just 3, so signal shape will come like that. We a little bit said earlier that we have this term 3 cosine squared theta minus 1. So very basic mathematics will tell you if an angle is at a given value, and this value is 54.7, this interaction will be 0. So that's why in the literature it's called magic angle. And spinning, why would we spin? Because we want to emulate situation in solution, because solution state, free tumbling, I said, gives to averaging. So we get a simple signal, right? And rotation obviously will have a lot to do. And Professor Mali will show you why we would sometimes rotate very fast to get very detailed information. So proof, if this is a glycine, there are 2 carbons, clearly we see carbonyl and we see C alpha, right? And we say, wow, wonderful, we got the right compound. But if you want to understand how do they orient, what's the angle with respect to something else, you want to go back to this state. And he will be talking, I'm sure, about recoupling and all these fancy ways to restore this information, you see, because this will tell you about dipole-dipole interaction and so on. A little note, Oh, sorry, this is also in Slovenian, but this was a big excitement. It's now like even a little bit more than 10 years ago when Professor Meyer from ETH for amyloid, piece of amyloid, was able to use solid state NMR experiments only with quite a bit of isotopic labeling. But what they at that time showed how these protofibrils that are important for all sorts of diseases, mad cow disease, Alzheimer, all this, when proteins form these beta-rich structures, how do they sort of look, how do they assemble, and so on, of course, providing structural insight in these diseases that are, of course, still a big thing for all of us. So let me finish. This is the final slide. When you start reading NMR, please consider this is an ethanol and this is spectrum from the 50s. Believe me, we are very far from there. We don't look at oscilloscope to understand is there something, is there a splitting or no splitting. And there are many, many fancy ways that maybe dynamic polarization, all these fancy experiments that we would do. So NMR, wonderful thing to screen, to get high resolution insight. And obviously you have dedicated lecture. You do magic angle spinning, I think you will understand now, and rotor size, and Professor Wali will explain why would you sometimes spin at few kilohertz, why would you go above 100 kilohertz. And with this, I'll finish here. I think it's almost exact time. Sorry, it was a bit fast, and of course, you're more than welcome to ask any question. Thank you.